The previous lecture ended with a rather difficult algorithmic challenge that we will try to solve using the Burrows-Wheeler transform and suffix array. Let's start with the Burrows-Wheeler transform. Allow me to slightly change the focus. Instead of pattern matching, we'll talk about text compression. And run length encoding is the simplest way to compress a text where a run of a single symbol is substituted by the number of times the symbol appeared in this run followed by the symbol itself. You may be wondering why we want to do run length encoding for genomes, because genomes don't have many runs, but they do have many repeats. For example, more than half of human genome is formed by repetitive DNA, and the lion's share of many plant genomes is formed also by various types of repeats. But here's the idea. Let's convert text into something else so that our repeats will be converted into runs. We'll start from the genome, then we'll turn it into converted genome, and then we will apply run length encoding to the converted genome, because our hope is that converted genome will have many runs. Let me show how we can accomplish this. So let's consider all cyclic rotation of our favorite string Panama bananas. We start from this one, add this one, and continue. We form all cyclic rotation of this string. And then, after we generated all the cyclic rotations, let's sort them. The dollar sign is viewed as the first letter of the alphabet, even before A, so we start with dollar Panama bananas, continue, 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 and finally we'll have a sorted list of all suffixes of the text. You may be wondering why we are doing this, but look at this strange thing. If we look at the last column of the resulting array, and the last column of the resulting array is called the Burrows-Wheeler Transform of the text, that you will notice that also our original string Panama bananas didn't have many runs. The Burrows-Wheeler Transform of this string actually has many runs. For example, here's a run of 5a in the Burrows-Wheeler Transform of our original text. How have we achieved it? Let me explain it by using an example from the famous double helix paper by Watson and Crick, where they first presented the structure of DNA. And these are just some consecutive strings in Burrows-Wheeler Transform of this book, and you see that there are many runs of A in the Burrows-Wheeler Transform of this text. Why there are many runs of A? Well, one of the most common words in English is and. And every time you have and in the text, it is likely to contribute to a run of A in the Burrows-Wheeler Transform, as you see in this example. So our goal now is to start from the genome, apply Burrows-Wheeler Transform to the genome, and we can now hopefully compress Burrows-Wheeler Transform of the genome. And after applying this compression, we will greatly reduce memory for storing our genome. But it only makes sense if we can invert this transformation. And from compression version of Burrows-Wheeler Transform, we can easily go back to the original Burrows-Wheeler Transform. But can we go back from the Burrows-Wheeler Transform of the genome to the genome itself? Is it even possible?